All right, so new week, new problems. I'm going to start with number 83 from page 345. It says to draw orbital diagrams representing the ground state electron configuration for each of the following elements. And I'm just going to do one of the elements because every question from this set of problems was really repetitive, and it won't make much sense for me or really help you to go overboard with solving every single part. So I'm going to basically do the toughest part from each question, and then hopefully that helps you. So the first thing I would do is actually write the electron configuration. And so to do that, we got to remember that krypton is right here on the periodic table. And I'm going to do the longhand configuration because we want to do the entire atomic orbital diagram set. So if we're doing the longhand configuration, we're going to start at 1s2, and we're going to go to the second row here now, 2s2, over here to the p block, 2p6. Now we're down to the third row, 3s2, over here to the p block, right there, 3p6. Now we're going to go to the row that krypton is in, fourth row. So 4s2, after 4s we go back and fill 3d10, and then we end our configuration with 4p6. Now remember, this principle that we're showing here, we're going to show two of them. The Aufbau Principle was the first. With the Aufbau Principle, it means that you need to start in the lowest possible energy level, which is 1s, and build all the way up from there. So I'm going to start drawing some of the orbitals. This is a 1s orbital. There's 2s. We got 2p orbitals. Then we get to the third energy level. We got 3s. We got 3p orbitals, 4s, and then we fill 3d. And mine may not look exactly like the book does, but you get the idea. And then we got 4p. All right, so we're going to go ahead and place our electrons in there. And remember, when you place electrons in an orbital diagram, you have to do it using Hund's rule, okay? And I'll show you when we get to the 2p orbital what that means. So here are my two electrons for 1s. Remember, they have opposite spins, which is why the arrows are going opposite directions. 2s, and here's Hund's rule. You put one electron in each orbital first, and then we go back and we start pairing them up. Now we go to 3s, 3p. Again, we have Hund's rule placement right here. 4s, 3d. Now we go back and pair. My arrows don't look good at all, but whatevs. 2, 3, 4, 5, 6. And that's your atomic orbital. Something I just want to add on to this particular problem is you got to remember that krypton's a noble gas. Remember, noble gases do not like to react with other elements in any natural condition, and you kind of see why by looking at this particular diagram. Every single orbital is full, and every single electron is paired up. There just simply is not a need for getting any more electrons, gaining them, losing them, anything, which is why krypton is a noble gas. It doesn't like to react with anything. So this next problem, we are just writing expected electron configurations for the elements they said in this problem. These ones happen to be semiconductor metals. And I'm going to pick the two probably most complicated ones, or I'd say the longest ones out of here, which I'm going to be doing germanium and cadmium. Remember, it's a very repetitive process, so I feel like if it's not clicking yet for you, it will in a little bit as you see the patterns. So again, I'm going to do germanium first, and then I'll do cadmium second. And I'm going to do longhand configuration and shorthand configuration for both so you guys can see how that works. So let's start by just remembering where germanium is. Germanium is right here on a periodic table. So you can see how it's going to end. It's going to end as a 4p2 configuration. So we're going to go 1s2 to the second row now, 2s2, 2p6. Now we go to the third row. Remember, these rows correspond to energy levels inside of the atom. 3p6. Now we're in the fourth row where germanium actually is. 4s2, 3d10, 4p2. And we finally got to our box right there. So that's the full configuration. Now to do shorthand, you do not start with 1s. You actually start from a noble gas. And you always want to start in a noble gas that's up one row and all the way over to the right. And that particular noble gas is going to be argon. So in parentheses, we're going to write the symbol for argon. Again, argon's right here. We're going to continue our configuration from argon. So 4s2, 3d10, 4p2. And this works because argon's configuration is that. We just don't have to write it all over again. Now the next one was cadmium. Okay, this is a little bit bigger of an element. So on your periodic tables, let me erase that. Your periodic tables has cadmium right here. Okay, so you can see this configuration is going to end in 4d10. So let's get through that. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Now we're in the fifth row, 5s2, 4d10. That's the longhand configuration for cadmium. For its shorthand configuration, again, we go up one row all the way over to the right and start with that noble gas, which for cadmium is going to be krypton. Symbol for that is Kr. Again, really, Kr's configuration is all of that right there. So continuing from krypton, it's just going to be 5s2, 4d10. And that is your final answer for number 85, or at least those two elements. So 87 is just like 85. Again, just a lot of repetition with this, but it's meaningful in that it helps you memorize these elements in the configuration order pretty well. I'm going to just choose two of these, and I'll do two of the larger configurations for this problem. Again, you can check your answers in the back of the book. I'm going to do EU and PT, Einsteinium and platinum. And real quick on this particular problem, if you looked at your answers in the back of the book, it's going to give you like the actual configuration, or sorry, the expected configuration and then the actual. Ignore the actuals. They don't test you on stuff like that on the AP test. And the problem did tell you to write the expected configuration. So don't get mixed up on that. So Einsteinium is element 63, which is the sixth element in this row in the F block. So you can see how this configuration is going to end. And for this particular problem, using your table that I gave you guys in class should help out quite a bit. I'll do longhand and I'll do shorthand for each one of these. So starting with Einsteinium, we got 1s2, 2s2, 2p6, 3s2, 3p6. Now we go to the fourth row, 4s2. There's our exception here, 3d10, 4p6, 5s2, 4d10, 5p6. Now, sixth row is where it gets a little crazy. So we have 6s2. Again, that's right here. And you do put one electron in 5d1. But right after 5d1, you can see in this little spot, we're going to jump over here to the F block, and we're going to end with 4f6. Pretty crazy. I know. The shorthand. Now remember, we're dealing with elements that are technically in this row, the sixth row. So you're going to start from the noble gas that's up one row and all the way over here to the right. That one's going to be xenon. So we're going to put xenon in brackets and continue counting from there. So after xenon, you're going to go to the sixth row, so 6s2. Again, that weird 5d1. We only put one electron in there. And then we go over to 4f6. Platinum's even bigger than this one. So we are going to be choosing an element for platinum that is in the 6th row still. However, let me erase this so it's not so sloppy. It's not going to be in the F block. It's going to be in the 5D part of the periodic table. So we are looking at platinum right here. Okay, so that's where we're going to be stopping. We'll do longhand and then we'll do shorthand afterwards. So longhand, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. Now we're in the 6th row, so 6s2. Now, we are actually going to be filling up the entire F block. So I'm actually going to be putting that first since it gets filled. So 4F14. All right, we're going to fill all that up. Then we go and fill up the D block next. So 5D8. So just like the previous problem, the noble gas we want to start with is up one row and all the way to the right from here, and that's xenon also. So we're going to put xenon in brackets. And then from xenon, we've got 6s2, 4f14, 5d8. So again, keep practicing these. Again, it's the same pattern over and over again. I find this to be really helpful to use this periodic table just to get that order down. Remember, you're not going to have that on a test or a quiz. So hopefully you guys are starting to get the order down just by looking at a periodic table or just kind of knowing the order yourself. And that's where you want to be, and that's why I assign so many of these problems so you can practice that.